record. There we go. All right. Almost everybody's here. Great. Oh, and also if you got your midterm report, if you got an email from me, check your school email, check your JCC email, and see if you got an email from me about your current grade. If you did, I'm asking you to respond. Just how we plan on if things are not going well. Go ahead and respond to that. Let me know what your plans are. If you're going to stay in the class or not. All right. So, where did we leave off? So, we have in that email, let's spit this out. In that email, at the top where it had strengths or current things, yes, but you can see it in Blackboard. That course average in Blackboard is that has all the grades counted. So that's a good place. At the top of that list of, superlatives, things you're doing right, the first line is the letter grade that you have. I didn't put a number in the midterm report, but I did use that average from Blackboard to do it. So if you did not find the midterm report, I got them emailed to me. Check your JCC email, and maybe you'll find one there too. All right. So, like I said, last time, increasing, decreasing, constant functions. Where is it increasing? Where is it? I did, Andrew. Yeah. So that should be in your email as well. So we talked about that. We talked about symmetry. We talked about even and odd, and then we talked about mins and maxes. And we put it all together, and we found out that when a function changes its behavior from increasing to decreasing, that's where we will find a relative max. And when a function changes behavior from decreasing to increasing, that's where we're going to find a relative min. So we got 2 more examples, and this last page is just that definition again of intervals increasing, decreasing, and constant. And the definition down below of a relative max and a min. So we're finally putting it all together, because it turns out, like I said, that the relative max, the relative min, and all of this content is based on intervals. And we have the mathematical definition here, but we can also think of it, if we think of this graphically, we're seeing maximums occur when we change behavior from increasing, decreasing. Minimums occur when I go from decreasing to increasing. All right, so here's the last problem. This is kind of putting everything together. So we're going to look at our base functions, our 8 base functions here, and we'll use the examples that are given, and we'll figure out where is it increasing, where is it decreasing, where is it constant, local max and min, and even, odd, or neither. So we're just going to deal with the 4 that are listed, and I put all the pictures over here so that you would see them. So I have the quadratic function. Okay, that's the first one here. So let's type that, the quadratic function. Talk about the 4, all the attributes of this. I think 24 is where you can start to see it. Yep. So increasing, decreasing, constant, relative max, relative min, even, odd, neither. Okay, so those are the things we're going to be asking about for the quadratic function. So looking at this quadratic function, f of x is equal to x squared. Where am I increasing? Where am I decreasing? Where am I constant? I'm increasing, starting at 0 and going on to the right forever. So increasing, I'm going to use the, I'm just going to type here instead of write. X is an element of, I start at 4, or sorry, start at 0, and I go to positive infinity. Oh, that used to. What is the prefix for that? IN, that's weird. INFTY. There we go. Okay. So quadratic functions increasing from 0 to 100, and this is not all quadratic functions. This is just the quadratic function that's in our basic table here. Where am I decreasing? Well, I stopped decreasing at 0, and where did I start? I've been doing it forever. So the decreasing, instead of positive infinity, it starts at negative infinity and goes until 0. And then where am I constant? This function's never constant, so there's none. Or you can just, yeah, just put none there. Do I have a relative max? Again, looking at this parabola, do I have a relative max? Nope. Because my function is decreasing and then increasing. Decreasing to increasing would result in a relative minimum. And that lowest value on that parabola is 0 when x equals 0. And it's even. Excellent. It is even because I have symmetry about the y-axis, or because f at negative x is equal to f at x. Right? I fold over from right to left, and the function will land right on top of itself. Okay. How about the cubic function? Let's bring it over here a little bit. Cubic function. Okay. This one's does some fun stuff as well. So let's look at the cubic. Okay, so where am I increasing on this? Okay. So, well, let me say it the other way. Where am I decreasing on this? Does this function ever fall from left to right? No, right? It does a little, it changes its concavity right here, but it doesn't change what its behavior is, if it's increasing, decreasing, or constant. This function's always increasing. So if a function is always increasing, then where is it increasing? Is the entire domain. There's no problems, you know, as if x goes off to negative infinity, nothing bad happens. As x goes off to positive infinity, nothing bad happens here. There's no possibility of division by 0. There's no negative under an even root. So that means the domain of this is all real numbers, negative infinity to positive infinity. So increasing, decreasing, constant. I'm increasing from negative infinity to infinity. I'm decreasing nowhere, and I'm constant nowhere. Okay. Now, do I have a relative max or a relative min? No, because why? Because the function's always increasing. Since it's always increasing, that means it never changes from increasing to decreasing, it never changes from decreasing to increasing, which means there are no relative max or mins in this one. So none for the relative max, none for the relative min. How about symmetry? Oop. Do I have any symmetry? I don't have symmetry about the y-axis, so I'm not even. How about the origin? If I rotate this 180 degrees, do I get the exact same function I started with? Yeah, I do, right? So that means I have symmetry about the origin, which means this function is odd. Now, remember what we said in a little shorthand the other day, the cubic function is f of x is equal to x cubed. So it's odd. Does that make sense? Yeah, the power is odd. All right, the power of x is odd here, and there's no other terms, so that means I'm odd. What does the quadratic function look like? It's x squared, and it's even, right? So quadratic, cubic, the other two, I think, are the cube root, yeah, cube root and the absolute value. I think it's cubed root function. So what is that? Well, cubed root is exactly what it looks like, cubed root of x. Now, let's go take a look at it, and then we'll talk about its behavior. Cubed root function is right here. Nope, it's cube root. Think about cube steak, apparently. Cube root. All right, so what is this function doing? Okay, well, it's always rising from left to right. It's never falling. Yeah, that's all it does is increase. Okay, so since all it does is increase, it's got the same property as the cubic. It's increasing everywhere. It's decreasing nowhere. It's constant nowhere. It has no relative max. And it has no relative min. How about its symmetry? It's not symmetric about the y-axis, so it's not even, but it is symmetric about the origin, so that means it's odd. Yep, exactly, so that one's odd too. We said this was none. I think I typed over the wrong one. Yep, that's right. And then the last one is the absolute value function. Absolute value is the v, and it looks like absolute value of x. Okay, what is it doing? Absolute value function is right here, number 7. This one does have increasing and decreasing characteristics, right? It's decreasing until 0 and then increasing on the other side of 0. There you go. So decreasing until we reach 0, increasing until we reach positive infinity. So let's write that. Increasing, that was 0 to positive infinity. Decreasing is it's coming in from the left, so that's negative infinity up to 0. It's not constant anywhere. And I know what you're thinking, hey, what about at 0, 0? It's constant there. A function's not increasing, decreasing, or constant at a single point. Increasing, decreasing, and constant has to occur over an interval. So if you're looking at the cube function or the cube root function and thinking, hey, it does that concavity change there at 0, 0, isn't it constant there? It can't be constant there. It can't be constant at a point. You have to be constant over an interval. Relative max, I don't have one of those, but I do have a relative min, right? And I know I have a relative min because I go from decreasing up until 0 to increasing. So I've got a relative min of 0 when x equals 0. And you already told me this one's even. You're absolutely right. because I have symmetry about the y-axis. Yeah, I just typed all of that. All right, let's fix that. That goes here. And all of this goes where? The quadratic, cubic, cube root, absolute value. All right. So there we go. Look at that. All 4 examples we chose are even or odd. But that's the first part of 1.7. All right. So let's go look at the second part. Okay. If there is a tough part of this section, it's this part. Okay. I don't know why piecewise defined functions are so difficult, but they are. Okay, I haven't quite cracked the code of what makes them so difficult. So why are they called piecewise? Because they are defined in pieces. Okay, I still have a function, meaning that I always pass the vertical line test. Okay, but depending on the x value, that determines, the x value determines which piece I pay attention to. Yes, graphing them in ALEKS can be difficult, and somebody stuck around and asked that question yesterday, so we definitely want to talk about that, right? So sometimes f of x is 3, sometimes f of x is x squared, and sometimes f of x is, it was you, yes, and sometimes f of x is equal to 2x minus 3. So on part of this graph, when f of x is equal to 3, that's going to be constant. When f of x is, sometimes it's going to be quadratic, sometimes it's going to be a parabola, and then sometimes it's going to be linear. So the question asks us to evaluate 5 different values. We're not going to try to draw it yet, but we do want to talk about it and see if we can make sense of this. So f at -2, all right? -2, what we do is we come over here and we look at our limiters here. Okay, when x is -2, which one of these 3 do I pay attention to? The first one, the second one, or the third one? Well, I pay attention to the values of x in my domains that contain the value I'm interested in. -2 is definitely between -3 and -1. So that means that I just pay attention to this part. And what am I supposed to get? I'm supposed to get 3. X is not involved, right? So once you figure out which limiter is the one that holds it, come over here to the right, and that's what gets put down. So at -1, this is when it gets interesting, when we start looking at endpoints. When x is -1, I'm still paying attention to this first row, right? Because x is greater than or equal to -1. So when x is -1, I get 3. When x is 1/3, 1/3 is not in the first set, but it is here in the second, right? Between -1 and 1, 1/3 lives there. So that means which function, which piece do I pay attention to? The second one. The second piece is x squared. Okay. Well, instead of x, I have 1/3. 1/3 squared is 1/9. And then the last one, f at 8. 8 is definitely down here in the third level. So when f is 8, I am looking at a linear equation. So that's 2 times 8 minus 3. 16 minus 3, which is 13. And then I think the last one, yeah, f at -3. Where is -3? Is -3, which one of those am I paying attention to? The first one, the second one, or the third one? Which one of those limiters contains x is -3? Good. Excellent job, Sarah. None of them do. The temptation is to say this first one does, but it doesn't because this is x is greater than -3. When x is -3, this function is not defined. So that's what we put. Is not defined. That does not mean we divide it by 0, like when it says something is undefined, okay? It just, there is no answer to the question, right? What is f when x is -3? The function doesn't accept -3. It's not part of the domain. Now, let's plot these things, and let's see if we can get an idea of what this looks like. So when f is -2, y is 3. So there's 1 point. I need to use when f is -2, y is 3. When f is -1, y is 3. When f is 1/3, or when x is 1/3, f is 1/9. That's going to be really tough to graph, so I'm going to go into a third, and then I need to go up a ninth. That's going to be really, really close to that value. I need a circle. Oh my goodness. Please stop doing that. All right. All right, so we're here. F at 8 is 13. That's off the graph. So f at 8 is 13. That'd be way up here. And then f at -3 is not defined. So what does this thing look like? Well, like I said, sometimes it's a parabola. Sometimes it's a line. Sometimes it's a constant function. So we're going to talk about how to graph it, and then we're going to come back and graph this one in the end. Okay. But before we do that, let's just do another example where we're just trying to get our idea of what do these look like, okay, and how do they work. So functions are given, use the graph and or the functions to evaluate each. So once again, I have 3 pieces. The function is in the first row, this is linear, right? Because that's a linear equation. The second row, this is quadratic because x is going to end up being squared. And then the last row, it's constant. Now, they don't always have to be different. They could all 3 be linear if they wanted to be. They could all 3 be constant if they wanted to be. So it's not a situation of it always has to be this way. It just happens that the 2 examples we've done so far, all 3 are different. Now, take a look at what that looks like. So here's the graph of that. F of x equal to -2x minus 4 when x is less than -1. X is -1 is here, and there it is. There's that line, -2x minus 4. And then it stops, right? The line stops right here. And then once I reach -1, I'm paying attention to this equation. This is a parabola. The leading coefficient is negative, so that means it's a parabola that faces down. All right. And I use that parabola that faces down from x is -1 up until x is 5. Now, take a look at this. When x is less than 5, that means including -1, but not including 5. 5 is actually down here. So how do I represent x is less than 5 without actually putting something on 5? I use that open circle. Exactly. I have to use the open circle, and it tells the reader that I pay attention to this quadratic all the way up until I get to 5, but not including 5. Now, in the last part, when x is 5, I'm supposed to put 2. So when x is 5, I'm supposed to get 2. Take a look at that dot. That dot is filled in. Okay. Am I still a function? Do I still pass the vertical line test? Yes. The only place, whenever you have a piecewise, the place that's going to be the most confusing is always going to be where these limiters, where the first one ends, the second one begins, and where the second one ends and the third one begins. And that's exactly what happened here. This one, they happen to match up. This one, they did not, right? This gives out at 4, at y is 4, and then this one picks up at y is 2. So this one's open, this one's closed. If I draw a vertical line through my graph, I still only hit the function once. I hit it right there in that solid part. All right, so what? Yes, not continuous, exactly, not continuous, right? I have to pick up the pencil or pen to draw the rest of it. So what's f at -2? -2 is here in the first one, right? So x is less than -1. That means I pay attention to the top row. And the top row says, pay attention to the linear equation here, -2x minus 4. And then for x, plug in -2. 4 minus 4 is 0. Now let's go look at the graph. When x is -1, excuse me, when x is -2, what is y? It's 0. So if you get a graph of a piecewise function, you can use the graph to solve it, or you can use the equation, the actual piecewise function equations to solve it. What about f at 3? When f is 3, 3 is between -1 and 5. So that means I'm paying attention to this second one. And then no one's happy about this one. X minus 3 squared plus 6. Plug in 3 for x, and then something neat happens this time. 3 minus 3 is 0. 0 squared is 0. 0 times -1/2 is 0. 0 plus 6 is 6. On the graph, when x is 3, f of x is 6. Okay, how about f at 12? Okay, 12 is off the graph, so I can't go to the graph and look at it. I have to use the equation. When x is greater than or equal to 5, the answer is 2. Okay, and that is all controlled by the left hand, by the limiters on the right. And then lastly, f at 5. When x is 5, I'm paying attention to the third row again. I get 2. All right. Now, here's the interesting part. Okay. What is the domain? So the domain of a piecewise defined function is the union of all the limiters in the problem. So for us, let's see what we have. So when x is less than -1, what does that look like in interval notation? Yep. So that starts out at -infinity and goes up to -1. It does not include the -1, so we put a parenthesis. The next one is from -1 less than or equal to x less than 5. What does that look like in interval notation? It starts at -1, it goes until 5. I include the -1 because my inequality on that side has equality, but on the right, the 5 is not included. And then the last one is x is greater than or equal to 5. In interval notation, that looks like 5 to positive infinity. So the domain is, put all of these together, negative infinity to -1, union -1 to 5, union 5 to infinity. Now, if the endpoints match up on these intervals, and one of them has it, one of them doesn't, I can actually put them together. Okay, so the first interval starts at negative infinity, goes up until -1. The next interval picks up at -1 and goes until 5. I can combine these. That's negative infinity to 5 because there's no numbers between negative infinity and 5 that are not included. And then what about the second and the third one? Well, that ends just to the left of 5, and this one picks up at 5. So these two are right, these are side by side. So it turns out that this is everything. Now, the first problem would not be negative infinity to infinity because it doesn't, remember we had that, the function's not defined when x is -3. It would not be all real numbers. Yep. Now, if any values are missing in those limiters, if say one of them is, let me just give you one. If I said when x is less than 3, do this. When x is greater than 3, do this. We're missing 3. And anytime you're missing a value, you have to leave these you have to leave the intervals non-combined, right? Because this would contain, so we negative infinity up to 3, and then this would be 3 to infinity. So when I put those together, union 3 to infinity, we're letting the reader know this is not all real numbers because there's a gap when x is 3. All right. So the domain is just the union of all of the intervals or all the limiters given. And if those limiters are side by side, you can combine them. In this case, it turns out you can combine all 3. All right. So piecewise, still fun. So let's go after the IRS. All right. So for 2010, federal income tax owed by a taxpayer, single no dependents, was based on the individual's taxable income. Okay. Anybody know what this is called? The kind of tax system that we use? No? Okay. It's called a progressive tax system. Okay. And why is it a progressive? Yes, Andrew, that's a good question. Why can't it be flat? So we want a progressive tax income because if you make very little money, let's just say it's 10%. Let's say the taxes are 10%. If you make, in this case, this is 2010, not even close to what it is now, but if you make $8,000, your tax rate, this would be 10%. If you made this, it'd be 10%. 10% of $8,000 is a larger portion of the person's income than 10% of, $100,000. So the idea is that the more you make, the more you pay, but because it's progressive, everybody follows these rules. So for the first $8,375, no one pays taxes on that. For the every dollar past $8,375 and up to $34,000, you pay a 15% tax on that. For anything over 34,000 up to 82,400, you pay 25% on that. So there's not a situation, when I thought about taxes, I was always bothered by the idea, well, what if I make 39,900, what if I make 33,999, then I have a 15% tax rate. But if I make $34,001, now I'm at 25. No, the first 30, that number between 8,375 and 34,000 only gets taxed at 15%. Okay. Yeah. So then that $1 I made extra gets taxed at 25%. Right? So no one pays taxes on their, the first income or the first bracket is always, this is how much you can make before the federal government says you need to pay anything. The next bracket is the 10%. The next bracket's the 15 or whatever the numbers are now. All right. So this is a piecewise function. And here it is. All right. Now let's see if you can make sense of it. Okay. So in my first row up there, if I make at least 0, but less than 8,375, I have no base tax. Okay, but I have a 10% rate. Like I said, this is not actually the IRS. These are not the IRS numbers now because that first gap doesn't have, you don't pay taxes on that first gap. But in this problem, we're supposed to pay 10%. All right, so if I land in this area, okay, I pay attention to this function. And this function says, take 10% of what you made, and what you made is between 0, is greater than 0, but less than 8,375. Next, let's say you make somewhere between 8,375 and up to $34,000. If you make it in this range, you're supposed to pay attention to the second tax rate. So that would be taxed at 15%. So that's what this is doing, right? For all the dollars over 8,375, you pay 15%. But we have this addition here. What is this? In this problem? Well, that $837.50, that is your base tax. That's the taxes you paid on that first $8,374. Right? So 10% of 8,375 is $837.50. So that's what it means by base tax. The first row has no base tax because you can't be below 0. The second row, if you made $42,000, you've made more than the first row. So that means you're paying 10% of the first 8,375, and then you're going to get picked up 15% for everything over that. And then in this one, we only have 3. The last one, if you make more than 34,000, but less than 82,400, 25% tax rate of all the money you made over 34,000. How do you do that? Well, if you made 60,000, 60,000 minus 34,000 is going to be 26,000. So you'll pay 25% tax on the 26,000. But then your base tax is going to be $4,681.25. What's this? This is the sum of all of the taxes you already paid. This is the $837.50 that you pay for the first one, and 15% of 30 of the difference of 15% of 34,000 minus 8,375. So that's what it means by the base tax. The base tax, so if you get up into the third bracket, the base tax is all the taxes you pay on all the brackets below that. So if you're in the 6th bracket, you have passed 5 brackets. So your base tax rate is going to be all of the taxes you pay on those first 5 brackets. All right. So we always want to find a good example if we can find one. This is decent. It's still not super great. I didn't do a problem with it. I just wanted to introduce taxes to you. I wanted you to understand or just start talking about them and try to give you a real example. All right. So we have some application or we have some problems here where the next two, they want us to graph. So r of x is equal to x squared minus 4 for x is less than or equal to 2, 2x minus 4 for x greater than 2. And then the next one is another piecewise function, s of x. It wants you to graph these two. So I've got to take a break. And when I come back, I want you to work on these two and let's see what you come up with. All right. Any luck? Ideas? Okay. So for these problems, I've got, when I have the piecewise function, the first thing I'm going to do is I got to figure out what am I looking at in these two pieces? Okay. Send the image. Yeah, send the image, Andrew, through the chat. Doesn't? Oh. I thought it had a, if I could send an image. That's okay. We'll just talk through it. No, that's okay. We'll just talk through it together. We'll see. Let's see if yours matches up. You can check that. All right. So the first one, this is quadratic. And this piece is linear. All right. Why is it important to know which one is which, or what we have? Well, because if I want to draw a quadratic, which is going to graph as a parabola, I need 3 unique points. I got to give it 3 points before I can draw a unique parabola. For a linear equation, I only need 2. All right. So the first thing I'm going to do is just pick 2 points in the intervals or in the limits so that I can plot them. So x is less than or equal to 2. Let's make life super easy. Let's pick 1. 1 squared minus 4. 1 minus 4, which is negative 3. And then 0. That is 0 squared minus 4, which is 0 minus 4, which is negative 4. So at 1, negative 3, I have a point. I don't know why it does that. You did it backwards. And then 0, negative 4. Okay, so we said this is quadratic, so we need another one. What's r at negative 1? Negative 1 squared is 1. 1 minus 4 is negative 3. So we start our way back up. Okay, so there's my parabola. Now, where does it stop? Okay, what's the last point for that quadratic? The last value where I'm going to pay attention to this is 2. Okay, when x is 2, I get 0. So at 2, I get 0. And this is part of that graph because it's less than or equal to 2. So there it is. So I have this. I can draw a unique parabola using that. So from here, we're going to come down. We're going to hit these 3. We're going to go back up. And we're just going to continue that behavior forever. Again, graphing, yeah, you would definitely want to use some software on that because that's horrible, I know. So now let's look at the other piece. The other piece is when x is greater than 2. So when x is greater than 3, like 3, 2 times 3 minus 4, 6 minus 4, which is 2. So when I'm at 3, when I plug in 3, I get out 2. Let's try 4. When I plug in 4, I get out 4. So 4, 4. Okay. Now, where did I start paying attention to this equation? I started when x is greater than 2. So here's the tough part to remember about this problem. So I'm going to pretend that this piece is defined at x equals 2, then enter an open circle at it. What does that mean? So I'm pretending that pretending is equal to 2 times 2 minus 4. Yeah, I didn't count right. 4, 4, that makes more sense. Okay, there we go. All right, so this is the pretend. 2 times 2 is 4. 4 minus 4 is 0. So when when x is 2, y is 0, and this gets an open circle. All right, so at 2, 0, I have an open circle. Well, it turns out these pieces this piecewise function is continuous because where it stops paying attention to the quadratic, it starts paying attention to the linear equation. And then I'll add my line passing through those 3 points. Now, you could just use the endpoint as one of the two, but I think it's better for us to consider it, pick some points that definitely work, that fit on our graph, and then we come back to those endpoint, or we come back to those interesting points. What this means for these piecewise functions is you're always going to graph the points wherever one limit begins, one limit ends, and the next limit begins and ends. So in this case, the only number, the place where we stop paying attention to the quadratic and start paying attention to the linear is when x is 2. So when x is 2, I'm going to plug it in for the first one because 2 is actually in this limit. And then I'm going to plug it in for here, pretending this is defined at 2. And then the result of that's going to be an open circle. Why do I need to do that? Well, it's because 2x minus 4 for x greater than 2, the only way to plot all the numbers for x is greater than 2 is to have an open circle at 2 and then draw the line straight from there. Okay, it's the interval notation stuff where we have to use a parenthesis instead of a bracket. I can't have that included. So that open circle is there, and then my closed circle's on the other piece. All right, let's look at another one. Okay, and also the parent functions that you've seen, they can be helpful. Okay, because you can get the idea of a general shape in that one. Had a quadratic, that's parabola. I had a linear equation, that's a line. So we kind of know what this is going to look like in the end. Now, so I have s at x, negative x minus 1 when x is less than or equal to negative 1. The square root of x plus 1 for x greater than negative 1. So let's go get some pieces of this. I'm going to try s at negative 2. So that is negative 2 minus 1, which is 2 minus 1, which is 1. And let's do negative 3. Negative 3 minus 1. 3 minus 1, which is 2. Is everybody okay with what I just did there? Does everybody see where I got those numbers from and how they're being plugged in? Just curious what that did. Anybody having trouble with that? Oh, okay. Anyone else? All right, so let's plot those. This is linear, so I just need 2 points. I can draw my unique line. So that's -2, +1, right there, and -3, +2. All right, so there are my 2 points. The resulting function is a straight line. Where, and we can go ahead and deal with this, where do I stop paying attention to that top row? I stop paying attention to it after x is -1. Now it's included, so that's minus, negative, -1, -1, 1 minus 1, which is 0. So this is my end point. -1 is included in this limit, so that means this is a closed circle. And it goes right there, -1, 0. Okay. With those 3 pieces, or excuse me, 3 pieces, with those 3 points, I can now draw the line that I need. All right. I know this is the super fun part of class, is watching me struggle with technology. But there we go. So there's our line. It's not perfect, but you get the idea. What about the other part? What kind of function is that? Okay, we've dealt with quadratics, we've dealt with linear equations, we've even seen cubics, but this is a square root. All right, so the square root of x plus 1, what does that look like? We have to go back to our original, to our basic 8 here, and take a look. The square root function looks like this. It's a slow rise from left to right. So I'm going to need 3 points on this one to draw it. So let's go find those points. And those are when x is greater than -1. So -2 means -2 plus 1. Oh gosh, what did I do there? That's the square root of -1, which is undefined. What did I do wrong here? Any ideas? What's wrong? Why did I get something that's undefined? Sometimes it means that's the answer, and then sometimes it means I made a mistake. Which one is this? Okay. Well, I plugged in -2. -2 is in my first set of limits. So this doesn't make sense, but it's not supposed to, because I need to pick numbers that are greater than -1. So the first integer greater than -1 is 0. Square root of 0 plus 1. 0 plus 1 is 1. The square root of 1 is 1. We don't do the plus minus here because I didn't take the square root of 2 sides of an equation. If you're ever wondering, why is it if I say the x squared is 49, then x is positive and negative square root of 49? That happens because I'm taking the square root of both sides. This side's a variable, this side's a number. So that's why when I take the square root of 1, I just get 1. All right, so 0 is the next point, and then 1, 1 plus 1 is the square root of 2. That's not really easy to graph. So instead of just picking integers, let's see if we can figure out what values of x would return some nice plottable points for me. So at 0, I'm at 1. At 1, I'm at the square root of 2, but again, that doesn't plot well. So the next square after 1 is 4, right? And the square root of 4 is 2. What do I need to plug in for x to make this equal the square root of 4? What value of x would be really useful here? Three. Yeah. So when x is 3, s of x is going to return 3 plus square root of 3 plus 1, which is the square root of 4, which is 2. So when I'm at 3, I'm at 2. And then we'll do one more. The graph, it does go on. So the next square is 9, right? So it'd be great if I could plug in 8. Because whatever number I plug in for x, I'm going to increase it by 1. And then take the square root. So when I'm at 8, I hit 3. And this is what I meant by this is a very slow growing function, right? It's got a little curve to it. It's not a straight line. It's growing, but it just does so really slowly. So there are my points, so I can get an idea of the graph. The last piece I have to consider is find the open circle of x is -1 for the square root of x plus 1, right? I know that when x is -1, I know I'm supposed to plug into that top row. But I have to do this graph, and I have to figure it out for all the points, all the way back to when x is -1, and I'm going to make a open circle there. So when x is -1, what would I get if I use this equation? Square root of 0, which is 0. So at -1, I'm at 0, which means that's another open circle. They're not always continuous, but the examples you've seen so far are. That's not too bad. And there's my piecewise function. So for part of it, it's linear. For part of it, it is square root. All right, so we'll call it there. The last two will be pretty simple. So ignore that the test will not be this weekend. The test will have to be the following weekend. It's going to take us a little bit more time in here, but that's what we're here for. I want you to learn the material, not just be able to not to rush through it and get you to the test as soon as possible. So any questions out there before? Yes, you will get a review for this. Olivia, yes, I will go over that. If you need to go, you're welcome to. I'm going to show, I'll keep recording. So if you do need to go, you'll have access to this. Because there is, where am I at? There we go. The problem that I want you to see is a piecewise with a graph where you have to tell the problem. You have to tell Alex that I know this is one piece of it, but it's not you graph the entire parabola and then you tell it, where do I stop paying attention to that function? So assignments 1.7. Preview. Question 5. All right, so suppose the function f is defined for all real numbers as follows. It's negative x squared plus 10 if x is greater than or equal to -4 and less than 4. It's -5 minus x if x is greater than or equal to 4. So this means the interesting point in this one is definitely when x is 4, because that's when we stop paying attention to one and start paying attention to the other. So let's plot these two. So the first one is a parabola. It's x squared negative x squared plus 10. So that means the negative out front takes the parabola and flips it over the x-axis. So now it's pointing down. So I start here, I end up pointing down, and then I move it up 10 units. So up, flip, and then I need another point so that I can, or some other points so that I can make it unique. So what happens when, I know what it is when x is 0. What about when x is 1? When x is 1, that's negative 1 plus 10, which is 9, which should be right there. And now I have my parabola. Okay? Now, when do I start and stop paying attention to it? Because notice this one does not start at negative infinity and go to positive infinity. This one actually picks up at negative 4. It starts at negative 4 and ends at positive 4. So I need to tell my function, okay, I'm not going to use this entire parabola. I'm just going to use this parabola for values when x is between negative 4 and 4. So that means I need to cut off when x is negative 4. What is f of x when x is negative 4? Negative 4 squared is positive 16. Positive 16 times negative 1 is negative 16. Negative 16 plus 10 is negative 6. So do I have 4 negative 6? Yep. And there it lines up. So I'm going to tell this thing to, what it's going to do is create a point at negative 4, negative 6. And it's going to plot it. All right. When do I stop paying attention to it in the other direction? I stop paying attention to it when x is 4. What happens when x is 4? 4 squared is 16. Negative 1 times 16 is negative 16. Negative 16 plus 10 is negative 6. So I need another cut when x is 4, y is negative 6. I'm going to plot that point. All right. So I know that this part of the parabola is not needed for my graph. And I know this part's not needed, right? This covers all the values of the function from x is negative 4 to positive 4. So once I've created those cuts, then I just go to the eraser and I bring it on top of the function. So I want to get rid of this tail and this tail. All right. Now, how about the endpoints? Okay. So this piece, when x is negative 4, I get negative 6. So I do need to put a solid dot on the end of that, right? But when x is 4, that's the other end of the parabola here, I have to put an open dot. And the reason for that is, why? Because negative 4 is included in this limit, 4 is not, right? So when x is negative 4, this is what I'm paying attention to. Now, let's do the other part. The other part is negative 5 minus x if x is greater than or equal to 4. Well, what do I get when I plug in 4 here? When I plug in 4, I get negative 5 minus 4, which is negative 9. So I'm going to go ahead and do my dot now. So at 4, I'm supposed to get back negative 9. So there's the first point. And then when x is 5, negative 5 minus 5 more is negative 10. I have my line, I have my 2 points, I plot them, and now once again, I have to cut this line. So where do I cut it? I cut it at the point where this all starts, which is 4, negative 9. So 4, negative 9. Plot that point, and then I'm erasing this side. right? So is this still a function? If it's a function, it still passes the vertical line test. Yes, this passes the vertical line test. Okay. The only place it would be in trouble is when x is 4, and we know that there's an open circle at one endpoint and a closed circle at another. Now, the last part of the question says, is the function f continuous? A function is continuous if you can draw the entire thing without lifting the pencil. You can't draw this parabola and this line without picking your pencil up, right? Not a brain teaser, you just can't do it. So no, this is not continuous because there's a gap. All right, check, and everybody's happy. All right. Anything else? Any other questions? No, 1-7. We'll move 1-7 and 1-8 to next week. All right. Okay, y'all have a great weekend. And I'll get the videos up.